कर लेता हूँ अपना क्वेश्चन।
Hello everyone. So in the last meet in the in the webinar, live webinar Zoom meet, we were not able to record it due to some technical glitches. So we decided to redo the slides and record it for you. So we'll upload this video on a YouTube channel. I mean, if you are viewing it, you might already have the access to it. So yeah, and all the slides and all those things will be given to you. If you have any doubts, you already know my number. You can WhatsApp me. Uh, yeah, as promised, let's recap a bit on the first webinar. So there we introduced you with the problem statement. We are giving you the slides. The link to the website will already available to you. I'll add this to the description also. Just make sure you check it. Also, the link to the registration is different, and the link to the registration for webinar is different. The link which we are circulating is a link to the what we say registration, and for the link to the webinar, you need to register here. This is the link to the registration. It will pop, like if you click here, it will slowly come. Yeah, a few things which I would like to point out in the problem statement is firstly, yeah, you're judged on the basis of your endurance. The more the time the glider flies, the more better, I mean, better score you get. And a few more things are you need to make sure you record the video properly as per the format given to you. And secondly, you also need to make sure that you follow all the COVID norms, and also you need to submit an abstract, by the way, where you need to show your approach to the problem statement. Okay, with that done, let me begin with the slides. Yeah, a few design constraints also that you should keep in mind is the wingspan should be less than 50 centimeter. You should not use a pre-built model of glider. You should make one yourself, and it should not be handheld sling type system. It should be placed on the ground and a button like system. We will discuss more on it because today I'll give you an example to the glider launching mechanism. Also, you make sure you do not use any electrical components because we will have some issues in judging you and all those things. Even electrically controlled ailerons and all those things are not allowed. It should be purely mechanical system. Not even a chemical stuff I mean, some fuel based stuff is also not allowed. So make sure you note those things. Basic materials required, I've listed it here. This is because many people were asking they are not able to access to the materials and all those things. So I have provided a list of online vendors which will give you some materials. I mean, there's obviously not a exhaustive list. There are many more vendors, but mostly these will do. And if you do not have access to these delivery systems of these vendors, you can contact to a local vendor and talk to him about the stuff available and all those things. If it is still not possible, you can contact us. We'll help you. So here's the glider launching mechanism. Yeah, so for glider launching mechanism, I'll not go into very depth of it. I'll just give you an example and cover it using that. A few things you should keep in mind is while making glider launching mechanism, make sure you have control of angle and speed. I mean, at till some point, obviously. So at least you have some estimate of angle and speed. That would help you a lot because you need to control those two things for modeling the endurance and all those things. This thing will be covered in the next webinar, which is on 19th, but yeah, make sure you have these things in mind. So this is an example taken from this research paper. You can go through it if you want. And yeah, so this type is an elastic cord, and as you can see, as we discussed, there were three types of elastic cord, spring, and compressed air. You can use either, but elastic cord, these guys have used elastic cord. This is the design. Have a look into the documentation if you want more detail of it. Yeah. So actually, the main thing I wanted to point out is, as you can see, this is a ground-based one. Yeah, it's a push-button mechanism. It's not, a slingshot-like mechanism where you hold it by your hand and release it. This is important because it will be used in judging you. So make sure you follow the rules. Okay, with that done, let's move on to the majority of the lecture. I mean, the major part is stability, because this will come in handy whether you are designing stabilizers, horizontal and vertical stabilizers, and these guys are important in when you like these carry a lot of weight, right? So you need to do these estimations of the dimensions and all those things. Okay, so let me like start with I mean, this is the last slide which was covered in webinar 1. Let me explain it again. So basically cm is the coefficient of movement, but you don't need to like I mean you confuse yourself with the notation. You just think it as a representation of movement, because rest of the stuff are anyway constant, I mean, in our discussion. So make sure like you understand this thing. Like to explain it to you, I'll show a few more things in the next slide. But this is basically a plot between movement and angle of attack. Yeah, and why it is stable, unstable, and neutral, let us discuss. The first thing is what is actually positive movement. Now, this thing is called pitch up, where nose goes up and tail goes down. Now, any movement that causes a pitch up, or like toward inside the plane for this case, that will be positive movement. Just something you should keep in mind. And second thing you should keep in mind is the stability. When what is stable, unstable, and neutrally stable. Now, when we talk about stable, we mean if we nudge it a bit, it will tend to like go back to its initial position. Neutrally stable is something if we nudge it, the position does not exactly change. And negative static stability is when nudged, it will go to a different position. So like keep this in mind. Now let's have a discussion on this graph. This is very important because this will come in handy to you in the later concepts also. So pay attention to this. Now suppose like now you are cruising in the equilibrium point, which is the trim point. Now suppose there is a like some turbulence and your plane suddenly pitched up a bit. Now because of that pitch up, now you want to make sure that like you provide a movement such that it pitches down and goes back to its trim point, because that's what stability is all about. Let us see what happens if it is a positively sloped moment angle of attack curve. So once it pitches up a bit, we see that movement provided is positive. But if we provide a positive movement and it's pitching up, it will tend to pitch up more. So that means it will actually go to a different state, not to a stable state. This is not what we want. So this is actually unstable. Like you can check this side of it also, negative and negative. Now let us look at the stable curve. Now if it pitches up a bit, we provide a negative movement. Negative movement will decrease the angle of attack, as I already talked to, like the pitch up is increase in angle of attack. So that will mean this is a stable plane. Now make sure you that's the reason this is stable, and make sure your glider follows this curve. And how would you make sure of that? Let's discuss in this like in the upcoming slides. One concept which you should know before going into the detailed maths is aerodynamic center. Now, aerodynamic center is more of a like theoretical stuff. The proof of existence can it can be easily done. You can like search it online. It's basically like there is a movement, positive movement at the one edge, and the negative movement at the other edge, and by IVP you can prove that there would be no change and all those things. It is like very easily done in various websites. You can have a look at it. So yeah, this is actually a point where movement does not get affected by angle of attack. So yeah, so actually it is helpful in the calculations, because then we can say like, yeah, it is independent of angle of attack, so we can calculate stuff here. It's usually at c/4 of the plane, wing. C/4 is quad by 4. So like if anyone has experience of RC plane, you will notice that a lot of times like you would be said that by your instructor or anyone who is guiding you that CG should match at CG should be at c/4. Now its significance will be clear to you in the upcoming slides. So let's see the moment like dynamic equation, which is the moment thing, torque equation. This equation is pretty trivial. You can actually solve it out using this. Like draw this figure and solve it out. It's not very difficult. We are just ignoring drag. Keep that in mind, because drag is in line with the moment. So that gets ignored. Yeah, so let's now this slide is basically to inform you why do we exactly need a tail. Now suppose you have a glider with only wing. Now where would you place CG and AC? Now suppose you have this configuration where AC is placed here and CG is placed here. So XAC is greater than XCG. The distance is measured from the leading edge. If XAC is greater than XCG, we see that this is negative. Now basically lift is like linearly dependent on the angle of attack, and the like positively linearly dependent. So like angle of attack increases, lift increases. So if you have a look at it in that sense, you'll see that movement and angle of attack will have a negative slope. So that makes sense, right? That's what exactly what we wanted. Now we wanted a stable glider, and negatively sloped, as we already discussed, is a stable glider. But one thing is something, I mean, there's something off here, and that is what will happen at the trim point, at the equilibrium point. At equilibrium point, moment of CG will be 0, and we see that lift will be negative because MAC is always negative. For cambered aircraft is negative, and for like symmetric it is 0, and that also we don't want. We don't want a 0 or negative lift for our glider, right? I mean, it won't fly. Okay, so that's an issue. How do we rectify it? Let's look at this. Maybe this situation will help us. In this way, in this XAC is less than XCG, so we immediately see that slope is positive and it's unstable. So this won't help us too. So that's the reason we use a tail. Now, what does a tail exactly do? So tail provides an extra lift, and there's an extra term added to the slope equation, which is this. Now, like how exactly it came, like you can check the maths. I mean, it's pretty trivial, but it's pretty long, so I am not covering it here. So you can check the math. It's available anywhere. If you want, I can send you the links. You can contact me for that. Yeah. So for this, now you can easily, I mean, manage CM naught such that like it is positive. You can adjust XCGA minus XAC. That's not an issue. Now, when this is positive, I mean, this has to be positive, this term. So this term has to be positive. Now, the main reason the entire term is negative is by adjusting this. Now, this is like adjusted. As you can see, the major contributing factor here is ratio of the areas and XACT minus XCG. This is called a moment arm. Now, this product is very important in making sure this becomes negative. This is basically the slope of the moment AC, moment and angle of attack curve. So, what we do is we take this parameter and non-dimensionalize it by dividing it with the this terms. For lateral, actually, this is not just for longitudinal. This is also for lateral case. If you follow the same procedure for the lateral case, that is for your horizontal stabilizer, you get these two equations. Now, when you have these two constants, now as you can see from these equations, by like comparing these equations and putting some values, some like values which are like commonly used in our RC planes and all those things, you will see that you will have a range of values for these two guys. These two guys are basically called tail volume ratios. So these tail volume ratios, you'll have a range of values again, which you can easily find from net, and from that you can actually design your plane. The range, I mean, from that range you can select a value, and you take that value and put it into the equation, and you will find the area of the tail, and you can like decide the aspect ratio and all those things, and you can easily design the tail. We'll cover more on that on the next lecture, but yeah, that's why these ratios are important. So what exactly are these ratios? I mean, intuitively, these are basically the non-dimensionalized form of the torque of on the tail. I mean, if you can look at it a bit more closely, it's more of a dimensionless torque. Okay, with that done, let us cover the rest of the part like of the stability. With stability, you can understand the concepts of neutral point. Now, what is exactly neutral point? As I already discussed in the wing only configuration, if you have AC and CG at the same point, which is this, basically the man denotes CG. So if you have XAC and XCG at the same, like AC and CG at the same point, you will have a zero slope. Now with slope being zero, it's a neutral point, like obviously. Neutral because you see, if you perturb it, there's no change in movement, so it will respond nothing. There will be no response to the perturbation. We generally don't desire it, but it is more of a limit point. And for a wing only configuration, AC and CG, I mean AC, if like for CG, the neutral point is AC, right? So make sure you like understood that. Now, but what happens in for like when you add a tail is the neutral point shifts a bit behind, I mean towards the tail. So when you place CG at AC, you are basically ahead of the neutral point, and you are in the safe region where it is stable. And the distance between the CG and the neutral point is called the static margin. Now, with a like bit of maths, you can show that static margin is basically like it's proportional to the slope of the CMCL curve. I mean CMCL directly relates to CM angle of attack. So, more the static margin, more the slope, negative slope. Now that's exactly what you want, right? More the negative slope, more stable your plane is. So yeah, make sure your static margin is good enough. Now, but like a question will arise is, so for increasing the static margin, what I'll do is just place CG as close to the nose as possible. Then we have the most stable plane, right? Well, that's not exactly true, because as we discussed in the last point, a stable plane can have a negative lift. And what exactly does that mean is this: the plane will simply drop. It is pretty stable, but it is just going down. So you don't want that, right? You want a stable plane, but also a plane which can like glide a distance, like it has some slope lift attached to it. By the way, this plane type of configuration is called nose heavy plane. So make sure you do not have build a nose heavy glider. Now, what if CG is behind the neutral point? What will that do? Well, it makes a very unstable glider, as you can see in the GIF. Make sure you do not make like not reach this configuration too, and this is called a tail heavy plane. So make sure your CG is in the right position, so that like it has a pretty, I mean it has a good amount of stability, and it does not have a nose heaviness also. Yeah, with that I end this lecture, and the important takeaway, I mean in this webinar, and the important takeaways are like this. You can like these things you should note it down or something, because it will come in handy in the next webinar. Thank you.